Okay, so we started looking at the decision problems for non-deterministic Büchi automata. Okay, the decision problems are about like so they are non-emptiness problem. Then we will look at non-universality and language containment problem. So again, what is the non-emptiness problem? So the idea of non-emptiness problem is that given an NBW, we want to check if the language accepted by the Büchi automaton is not empty. And similarly, the non-universality problem is to check whether it doesn't accept sigma omega, right? So it doesn't accept sigma omega. So that is the non-universality problem. And what is the language containment problem? What is the language containment problem?
Given two languages, is one is a subset of the other.
Yeah, yeah. So if you want, you can also switch on your video. I mean, I think it will just be easier. Uh, yeah, if you prefer.
Yeah, I will do
So
that. Just 1 minute.
yeah, yeah, yeah. So the language containment problem is like given two NBW, let's say A1 and A2, we would like to check if the language of A1 is a subset of language of A2. A1 is a subset of language of A2. So this is what is the language containment problem. And right, so we started with the non-emptiness problem for NBW in the last lecture. And this is what we claimed, that this is decidable in linear time and it is NL complete. Okay. So first, uh, let's see. I mean, let's uh, kind of try to see how you would decide that given an NBW, the language accepted by the NBW is non-empty. Okay. Uh, right.
Yeah.
Right. So how would you check that given a non-deterministic Büchi word automaton, the language accepted by the automaton is indeed it's non-empty? So how would you check in general? I mean, if you forget the complexity.
Uh, so we need the set of final states to be reachable, and from them we need a loop from one of the final states to another final state. Uh,
Why another final state? Why
assuming
another?
set of final states are connected, strongly connected,
Mhm.
I believe. Yeah, we
So
just need to show that it is strongly connected. That should be sufficient.
I mean, it's something which is quite simple. Like you start from some initial state, right? And from that initial state, as long as you can reach one of the queues belonging to the alpha, where alpha is the set of good states, right? And
Mm.
so the language is non-empty. When it is non-empty, if there exists some good state queue belonging to alpha, such that it is visited, like this good state queue is visited infinitely often,
Yes,
right?
that is sufficient. Yeah.
Hmm. So as long as you can start from some initial state q0 and you can reach some state q, which is a good state, and you can have a loop from q to q, then we say uh, we would say that it is indeed the language accepted by this given NBW is indeed non-empty. Okay, so uh, right, and why is it the case? Like, so suppose if it is the case that the language is indeed non-empty. So the claim was the following. So as long as, so this was the claim. So the language, accepted by the NBW is non-empty if and only if starting from some initial state you reach some good state and you can reach from the good state to itself. Okay, right? So why is this claim true? If it is the case that the language is non-empty, right? Then there exists some word. Then there exists some word such that starting from an initial state, it will reach a final state and it will loop, right? And so essentially, if you look at that uh, initial state, and if you consider the run, so there will be this particular, there will be one good state which will be reachable, and the good state will be reachable from itself, right? So this side is easy. And conversely, suppose if you have a state q0, which is an initial state, and there is some good state q which is reachable from q0, and you can come back to q from itself, then indeed you can consider like consider the labeling of the path. You can consider the labeling of the path, right, from q0 to q, and then you can like also consider the labeling of the path from q to itself, and you can find some word, find a path, and like you can find the word corresponding to those labelings. It will be an omega word, right? Like so, yeah, because you can come from q to q itself like infinitely often. And of course, that gives you that the language accepted by the automaton is non-empty. Clear? So this is this. So now uh, let's look at the complexity results. So we said that indeed this is NL complete and it can be decidable, like there exists a deterministic algorithm which is in linear time. So why is it the case that this is there exists an NL algorithm? How can you find an algorithm which is in NL? So what is non-deterministic log space algorithm? Like, so essentially like there is a non-deterministic Turing machine which uses only logarithmic space, logarithmic in the input size, logarithmic space in the input size, right? So,
Yeah, there will be two tapes in the Turing machine, and one is the work tape, and that will only take logarithmic.
okay, yes. So how can you decide this in NL? So how can you decide this in NL? So what all things you would need? So this NL machine will essentially guess, it will essentially guess a start state, right? And a good state, say a start state Q0 and a good state Q, and it will try to guess also a path and a path. It will also guess a path, right? And it will store the current state. It does not need to store the entire path. So what does it do? It stores, so first it considers the initial state, then it guesses the next state, then guesses the next state. So every time it just stores the current state, and it also stores a counter. Okay. It also stores a counter, right? If the state Q is reachable, then from Q0 to Q, it should reach within n steps, right? Within n steps. So the counter would keep like how many steps you are having. And if it is the case that you reach Q within n steps, right, then it will accept. Then the NL machine, the Turing machine would accept. Okay. So that's the thing. So this is what the NL algorithm does, and everything like guessing the initial state, guessing the final state, which here is Q, and then storing the value of the counter. Everything can be done in logarithmic space, non-deterministic logarithmic space. This is a non-deterministic machine. And then after that, it also checks another path that indeed from Q it can come back to Q, right? So it tries to see that it can come back from Q to itself, which is also in non-deterministic logarithmic space. It can do. Okay. Now we will show the hardness because it's NL complete is what we claimed. We also need to show that this is NL hard. How do you show that this is NL hard? So we would do a reduction from a canonical NL complete problem, which is like the reachability problem in directed graphs. Okay, reachability problem in directed graphs. So what is that? You are given a directed graph GE and two vertices S and T, and we check if there is a path from S to T. Okay, so this is how the graph is like, and we have an NBWA, and it has a set of vertices, and we say that you just need a simple alphabet, which has a single letter, singleton alphabet A, and delta is the transition relation. So how does delta look like given the graph? What are we trying to construct? We are constructing an NBW, non-deterministic Büchi word automaton. Given, right? Given the graph, we are constructing a non-deterministic Büchi word automaton, and it will essentially have all the edges of the graph. So that will, so this is what it says: delta V1A equal to V2 if the edge from V1 to V2 is there. Okay. And we also have on the state T, we have a self loop like this on A. Okay. So now you see that if indeed T is reachable from S, then the language is non-empty, right? If T is reachable from S, then the transitions in the NBW, what it will do, it will go from S to T. So there is some labeling of S from S to T, and then there is a self loop on T, right? So this is what it's doing. And so this is uh, indeed like if T is reachable from S, then the NBW that we constructed, it is non-empty, right? And the other way around. If T is not reachable, then the NBW will not accept any word, right? Hence it's empty. Clear? Okay. Now, what about the deterministic linear time algorithm? You can do something called, you can essentially have uh, the deterministic linear time algorithm, you can do something called an SCC decomposition. So you can, so you know what is an SCC? It's a strongly connected component. Strongly connected component. So these are the set of vertices which are reachable from each other. Okay, so you do the SCC decomposition. So essentially the maximal strongly connected component. So you can do this in linear time. And there can be trivial SCCs also. So trivial SCC is one which has just a single vertex. Okay, trivial SCC has a single vertex. Now, all we are saying is that we should find, there should exist some SCC with some initial vertex. So there should be an SCC S such that Q0 belongs to this SCC S. Okay. And there should be another non-trivial SCC, right? Let's say that is some S prime, and there should be a Q belonging to alpha intersection S prime. Okay. And we should say that there should be a path from this SCC S to S prime, right? And that should suffice, right? Because if it is, if S prime is an SCC or if S is an SCC, then whatever vertices are there in that SCC, they are reachable from one another, including one is reachable from itself also, right? So as long as you have a path from SCCS to SCCS prime, that is sufficient. Because all the vertices, like you also need to say, right, like that Q is reachable from itself. But given that this is an SCC, it already implies that the vertices there in they're reachable from one another, and including a vertex is reachable from itself. Clear? Right? So that is the like this SCC decomposition can be done in linear time, and this gives a deterministic linear time algorithm. Clear? Okay, good. So now we will do this non-universality problem. The non-universality problem is essentially about uh, like what does it say again? The non-universality problem. It says that whether a given NBA, whether it the language of that NBA, it's the entire sigma omega. So that is the non-universality problem. Okay. Now you see that the non-universality problem and the non-emptiness problem are somewhat related in the following sense. How? That an NBWA is non-universal if and only if its complement automaton A prime is non-empty. Okay. It's non-universal if and only if the complement problem is non-empty. So we have already seen uh, how to check like uh, the non-emptiness problem that we saw how to check it, right? And we say that a given NBW is non-universal if and only if the complement A prime is non-empty. Now, what would you do in order to check if given NBWA is non-universal? What we would do is that we would consider the complement automaton A prime, right? And see if the language accepted by this is non-empty. Now, if you recall that the given an NBW, what was the size of the complement automaton? What is the size of the complement automaton?
That is a exponential blow.
Yeah, there is an exponential blow up, but it was like 2 raised to n log n,
And
right? It was like order 2 raised to n log n, the complement automaton, correct? Uh, Now, of course, you see that what one could do in deterministically, is to construct the entire complement automaton 2 raised to n log n. So which is like there is an exponential blow up, and then also do the emptiness check of that complement automaton in linear time, which gives you an exponential time algorithm, right? But on the other hand, what we claim is that uh, this problem is indeed p-space complete. So we should try to give a p-space algorithm, right? So we should try to give a p-space algorithm, right? So what does the p-space algorithm, what does it do? So essentially it will be a non-deterministic. So we'll think of a non-deterministic p-space Turing machine, non-deterministic p-space Turing machine, right? So what does it do? It does not store or compute the entire complement automaton, which is exponential in size, right? It will not do that. But it will sort of guess which parts in that complement automaton, is sort of required to check the non-emptiness, and it will only construct those parts, those small parts, which it can do in logarithmic space of the size of the complement automaton, right? It can do that in logarithmic space of the size of the complement automaton. Now, the size of the complement automaton is already exponential, and logarithmic space in the size of the complement automaton is like, so hence it can do this in polynomial space, right? So this is something called an on-the-fly construction in general, on-the-fly construction. So it does not sort of construct the entire NBW, it will only guess the relevant parts, and it will try to the relevant parts which will be used to show the non-emptiness of the complement automaton, right? And what does it then would it need to guess? It will just need to, in order to show the non-emptiness, it will just store some of the states, right? It will just store some of the states, right? The initial state, the final state, right? The good state, and it will store the current state, and it will also have to keep a counter, right? It will also have to keep a counter. Now, all these can be done in polynomial space. Why polynomial space? Because you see that you have this many number of states. You have this many number of states, right? So if you want to encode a single state here, how much space you need? N log n. N log n space you would need, right? And that is like polynomial. N log n is polynomial space you would need. So to have an initial state, to have a final state, to have the current state, and the counter, right? So the counter, right? The counter will say what is the maximum length of the path from an initial state to a final state. So everything can be done in polynomial space, right? So we have a polynomial space uh, algorithm. Clear? For checking non-universality of NBW. Okay. Now we show. Now we need to show the p-space hardness of this problem. We need to show the p-space hardness. So there are different ways to show p-space hardness. You can also possibly do a reduction from. I mean, you can also do a reduction from Turing machines, like polynomial space Turing machine, right? And now, uh, um, right? So one can also do a reduction from um, the polynomial space Turing machine. So one can do that, right? Uh, one can also think of another problem, which we are going to look at here, which is like a reduction from the non-universality of NFA. Okay, so the reduction from the non-universality of NFA. So what is the non-universality of NFA? That given an NFA, it does not accept the language sigma star, right? NFA is over finite words. It does not accept the language sigma star. So that is the non-universality of NFA. Now, let's see how we would like to do the reduction. So one of the things is that, like, consider that, I mean, in general, if you just treat the NFA as an NBW, right? I mean, this may not be sufficient in the sense that it's like you may need to make some changes to the transitions and so on, right? Which may not always be good. I mean, you should think over this. So this will be a question like later, maybe a homework question. So what we will do is like, so whatever transitions are there, so all transitions in the NFA, so what we are going to do, so we are going to construct an NBW, okay? And we will say that if my given NFA accepts sigma star, then the constructed NBW will accept sigma omega, right? And vice versa. It will accept sigma omega and vice versa, right? So we are doing a reduction. Given an NFA, we are constructing an NBW, okay? Now all the transitions of the NFA, we will store in the constructed NBW. In addition, we are going to have a sigma prime, which will be sigma union this sharp symbol. Sigma union the sharp symbol, okay? So what is the idea? From every final state in the NFA, we will have a sharp symbol, and we'll go to a state which will be our new final state, QF, the new good state, right? So this is no longer a no longer a good state, but this QF belongs to the alpha. Okay. And here we will have sigma prime on the, we will have a self loop on sigma prime. We will have a self loop on sigma prime. So now, if that is the case, what is the language which is, suppose the given NFA is, let's say, N, and the constructed NBW is, let's say, A, right? So what is the language which will be accepted uh, by this NBWA?
So I don't understand this
The
construction.
construction. Okay.
Yes, this is a final state, and from there we are moving on a.
So you have some states in the NFA, of course, right? You have some states in the NFA. So all transitions of the NFA are preserved. All the transitions of the NFA are preserved. And then what we are saying is that you have we introduce a new letter, which is sharp, and we take from every final state of the NFA, we add the sharp symbol, right? We have a new transition to a new state called QF, where QF is a final state or a good state of the NBW, right? And there is a sharp symbol, and you reach there, and from the this thing, you have the sigma prime. Okay.
I understand.
So yeah. Um, so that's the thing. Now, so you understood the construction, right? How I am constructing the NBW. So there is a new symbol, there is a new state, and this new state is my only good state in the NBW. And there is a self loop which is sigma prime, right? Now, what is the language of the automaton A, which is the NBW? What is the language?
Whatever language is recognized by the NFA, and then followed by a hash, and then whatever is there
Right,
in the loop.
right. So then U belongs to, like it's sigma star, it's the language of N. So this is belongs to sigma star, of course, right?
Mhm.
So just to say that this belongs to also sigma star, and V belongs to
Sigma.
sigma prime omega, correct? Because you have this entire this loop over all the letters in the alphabet in sigma prime, correct? Now you see that if the NFA N is universal, is it the case that A is universal? We wanted that, but is it the case? Is it true that if N is universal, then A is also universal?
Uh, Maybe just the hash symbol,
Very good.
hash
Yeah.
omega won't work. Yeah.
Sorry?
Just hash omega, that word. Infinitely
No,
many.
that word, that word may be there also, right? I mean, for example, let's say if this is universal, if LA is
Then the empty
universal,
word will accept in the
then the
NFA.
empty word will be accepted, and then hash omega will also be there.
Will accept.
But
Yeah.
there are some other kinds of words which are still not there in LA, even if N is universal.
Okay.
What are those words? What are those words?
We need at least one hash in this language.
Exactly. We
Yeah.
need at least one hash in this language. So the words which do not have a sharp or the hash symbol, they are still not there. Okay.
Yeah.
So in order to do that, what we can do is that you can add another initial as well as final state or good state, say Q I, something like this. And then you can just say that I will add to this everything in sigma, right? This is also a good state. Okay. So QF is a good state. So alpha equal to now QF and this QI. Okay. So now we see that A is universal if and only if N is universal. Okay. Clear? So I'll just sort of formally state the how the transition relations look like, right? So this is my NFA. This is the given NFA, Q sigma Q0 delta F. Then we are considering the NBWA, which is of this form, uh, Q sharp. Okay, I think, uh, yeah. So this is the initial construction that I said without this QI. I mean, that QF is the same as the Q sharp here. So yeah, right? So I can maybe, let me call it Q sharp, right? So that is the thing. Then I said sigma prime or sigma sharp is sigma union this sharp symbol. Delta prime QA equal to delta QA. Delta prime Q sharp equal to Q sharp, right? So you have everything which is there in that sigma prime or sigma sharp, and delta sharp Q, that Q sharp A equal to Q sharp. Okay. So as I said that if you have only this, then if ln equal to sigma star, then la equal to u sharp v, where u belongs to sigma star and v belongs to sigma sharp omega. So A does not accept words not containing sharp. So in order to help that, we said we would add one more state, which is qi, and it's like delta prime of qi comma a equal to qi for a belonging to sigma. And here I would then have union qi, and this is also a good state, right? Union qi. Clear? Good. So, and you can see that if A is not universal, A is not universal, that means there exists some word U which is not part of the language of A, right? Part of the language of N. If there is some word, if N is not universal, if N is not universal, then there exists some U which does not belong to L of N. In that case, you also don't have the corresponding word U sharp V in the language of A, right? So we have this, that A is universal if and only if N is universal. Clear? Good. Okay, nice. So now let's look at another problem, which is the containment problem for NBWs. Containment problem for NBW. So the containment problem also, like what we are saying, that it is decidable in exponential time and is p-space complete. It is decidable in exponential time and is p-space complete. So how do you get a p-space algorithm now? So what is the containment problem again? So it's like we are given NBWs A1 and A2, right? A1 and A2. Check if L of A1 is a subset of L of A2. Okay. That is L of A1 intersection L of 2 equal to empty, right? Uh, Now that is the same as L of A1 intersection bar equal to empty, right? Where what is A2 bar? This is the complement automaton, okay, of A2, okay, right? And we can consider this itself, like A1 intersection A2 complement, to be an automaton itself, which is A prime. So we are essentially checking if L of A prime, if this is empty, right? And we would like to, uh, yeah, in order to check the emptiness of this automaton, so we would like to construct this automaton, right? So we need to construct A prime and check non-emptiness, check non-emptiness. Now, what is the size of A prime? What is the size of A prime? We are taking the intersection of two NBWs, and one is a complement of the given input NBW A2. What is its size? Size of A prime?
Uh, this 2 times the size of A1 and 2 to the power size of A2
Right.
log.
So, okay,
Is it?
good. So it's something like linear in the size of A1
Mhm.
and exponential in the size of A2,
Yeah.
right? 2 raised to n log n, order 2 raised to n log n, right? So overall, this is exponential in the size of the input, right?
Yeah.
And again, we don't construct the automaton A prime, but we have a non-deterministic p-space machine, p-space Turing machine, which does an on-the-fly construction, right? In order to, what does it mean? In order to check the non-emptiness, it guesses some initial state, some final state, and guesses a path. And all it needs to keep is like the current state, right? And a counter value, and a value of a counter. Everything can be done in polynomial space, as we saw in the case of the complementation problem, right? Now, just instead of just doing this for the complement automaton, we are doing this for the automaton A prime, which has the intersection of A1 and A2 complement.
Mhm.
Is it okay?
Yeah.
So everything can be done in non-deterministic p-space polynomial space. And now, I have been talking about non-deterministic polynomial space. Why non-deterministic polynomial space? Because the Turing machine guesses an initial state, guesses a final, guesses a good state, guesses a path, and it just takes one step at a time, right? And keeps the current state and keeps a counter value. So now, why did the case that non-deterministic Turing machine is the same polynomial space Turing machine? But we are talking about just p-space, right? We are not talking about non-deterministic p-space. The reason being, so there is a theorem called the Savage's theorem. So when you do your complexity theory course, you will see that the non-deterministic uh, polynomial space is the same as the deterministic polynomial space, right? NP space is the same as P space, right? Hence, this gives us also a deterministic polynomial space algorithm. This would, using Savage's theorem, you would also get a deterministic polynomial space algorithm, which may look slightly different. But given the fact that there exists a non-deterministic polynomial space algorithm, that implies that there exists a deterministic polynomial space algorithm, right? So uh, now we say that we can show the hardness, the p-space hardness, using a deduction from the universality problem or the non-universality problem. Okay. So I'm saying that my claim is the following. that the universality problem is a special case of the containment problem. The universality problem is a special case of the containment problem. Why is it so? Why is it so that the universality problem is a special case of the containment problem?
Consider the one of the languages to be the thing.
Right? So for example, I can ask, given an NBWA, right?
Ah,
If
yeah. Check
L
L of A1.
A
Uh,
equal to sigma omega, if and only if, sorry, I wrote said sigma omega, I wrote sigma star. If and only if sigma omega is contained in L of A, right? Correct? So L of A, so this is universal if and only if this is true, right? So which means that if you had an algorithm that solves the containment problem, you could have also solved the universality problem. Why? Because for this, you can just have a single state automaton with sigma. You can just have a single state automaton, right? And yeah, so, and this is like a simple, like a polynomial time reduction. So given that this problem we saw is p-space complete, this is a p-space complete problem, right? Given that this problem is p-space complete, this gives us that the containment problem is p-space hard. Clear? Right? So we are reducing the universality problem to the containment problem. So there is a small thing which I sort of put under the carpet, which is like we showed that the non-universality problem is p-space complete. But here we are doing a reduction from the universality problem, not the non-universality, but from the universality problem, right? So essentially, like, so we are saying that we are doing a reduction from the non-universality problem. Sorry, we are doing a reduction from the universality problem, right? So the non-universality problem is p-space complete. What about the universality problem? It's also p-space complete.
yeah, because if that Turing machine halts saying yes, then for the non-universality it will be a no, and vice versa.
That's not true indeed in general for non-deterministic Turing machines. It holds for deterministic Turing machines, but not for non-deterministic Turing machines, right?
Mhm.
Otherwise, you could have said that NP is the same as co-NP,
Okay.
right?
Yes.
Right? In fact, for NP and co-NP, we don't know whether such things exist or not. But it's for the NP space, it's true that we know that this is the same as the co-NP
Mhm.
space. NP equal to sorry, what did I, NP space equal to co-NP space, right? So, or yeah. Uh, okay. So our P space is the same as co-P space, right? So that comes from a theorem called the Immermann-Zellep-Sini theorem.
Mhm.
Okay. So that's the thing. Clear enough, the P space,
Yeah.
right? Okay, good. So this reduction is clear, right? It's a very simple reduction. We are reducing the universality problem to this um, to the containment problem. Okay, fine. Now, what about these problems when you consider DBWs instead of NBW? What about the complexity of these problems if you consider dBW instead of NBW?
We can obtain some upper bounds from doing the whatever determinization construction.
Let's say, first let's consider the non-emptiness problem.
Okay.
So the non-emptiness problem already so the upper bounds are, I mean, whatever upper bounds hold for NBW, they
Hmm.
already hold for DBW, right? Because NBW is like you are giving an algorithm for a general class.
Yeah,
So
yeah,
that algorithm also will work for the special class of DBW,
yeah,
right? The upper bounds anyway always hold
yeah.
for for like the NL for the non-emptiness problem. Already for NBW we saw it is in NL.
So here it's an.
Okay. What about the non-universality problem? Why is it in NL?
Mhm.
If you consider DBW, how did we do the non-universality of NBW?
Mhm. Where the non-determinism play a role?
So how did we? Oh, okay. So can we try to recall
Yeah.
our algorithm for the non-universality of NBW? What did we do?
Uh,
So we said that
we
A is
constructed the complement on the fly.
exactly,
Yeah.
yeah, A is non-universal
Mhm.
if and only if A prime is non-empty, where A prime is the complement automaton.
And we can construct a complement NBW given any DBW easily by
Exactly.
using the acceptance condition. Yeah. And
Well,
that will be an NBW, but it's possible, yes? No, 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 no. That's not true.
no, that's not true.
That's true.
But given a DBW,
Mhm.
given a DBW,
Mhm.
we can indeed construct a small NBW.
Yeah, yeah.
When I say small, what is the size of this NBW?
Or two times. We can
Two
make two
times,
copies
right?
and
We can make another extra copy. In that
Mhm.
extra copy, the alpha states, the good states of the DBW will not appear,
Yeah.
right? So this is linear in size,
Mhm.
right? And checking the non-emptiness is log space,
Yeah.
right? Checking the non-emptiness is log space, correct? So hence we have I mean, when I say log space, I say non-deterministic log space. I mean non-deterministic log space, right? So I have an NL algorithm for non-universality. Clear?
Mhm.
Is it okay?
Yeah.
I have an NL algorithm for non-universality. And similarly, can I also have a can I also have an NL algorithm for the containment problem for DBWs? Because you have to take the product, right? A1 subset of A2, A1 intersection A2 complement.
Yeah.
That product is also polynomial,
Yes. Yes.
something like quadratic, right?
Mhm.
And that also you can solve in non-deterministic log space of the input size. Clear? So the containment, so everything, non-emptiness, non-universality, containment, for everything for DBW there, you
Enough.
have non-deterministic uh, log space algorithms. What about the lower bounds? What about the lower bounds? So what about the non-emptiness?
The same argument with finding a path between two vertices holds here as well. Uh,
Exactly, right? Because if you recall, like, okay, I mean, if you recall, what did we have? Like we said that you had all the uh, we had a single letter here,
Mm.
and we had all the transitions. Like whatever age was there, you have like corresponding transitions.
Yes.
Now, will this work if I just have this? If I just have this reduction, will it work? What will be the problem? There was, suppose you had a vertex in the graph, like we are talking about this reachability from S to T. So there was a vertex, and the vertex, let's say, had three outgoing edges. In the
Mhm.
transitions, we are saying this also has an A, this also has an A, this also has an A in the corresponding NBW.
Yes.
This will not work. So what do you need to do?
Hmm. Check if there's a path from.
What do you need to do? If instead of a single letter, if you put here different letters to make it, you need it to be deterministic. You need it to
Mhm.
be a deterministic Büchi word automaton.
Yeah.
So now instead of these A's, I will keep different letters. How many more? How many letters do I need at most?
At most, the number of transitions that are there, the highest degree of any
Exactly. The highest outgoing degree, out degree,
probably. Yeah.
right? So that can be my alphabet size. And I get a deterministic automaton, right?
Right.
Clear? So for non-emptiness, we saw for non-emptiness, same reduction as, so again, or I can say reduction from reachability in a directed graph, but we need a alphabet size, larger alphabet, okay, whose size equals the largest out degree of a vertex in the graph. Good. So this is fine. Okay. So what about the non-universality?
Mm.
So I'm given a graph, right? Right. So what about the non-universality? I can do a reduction from non-reachability. It's exactly a very similar reduction. So it's like, I'll just briefly tell you how it works, and then you can try to find out the details. So you have S to T, right, in the graph, and I would say that uh, I will construct an NBW, let's say A. I'll say L of A equal to sigma omega. So the sigma will also be of the form like it will, uh, you have to, I mean, yeah, the sigma will also be, the size of the sigma will be at most the size of the uh, out, the largest out degree. So LA equal to sigma omega if and only if P is reachable from S. From S. Okay. Or that means LA is not equal to sigma omega if and only if P is not reachable from S. Right? Okay. So in fact, I can also make it in a way um, such that it can be even empty. Like if T is not reachable from S, you can make it empty. So think about this reduction. I mean, it's very similar to whatever we have done so far. I mean, it's just like, I think this is just a good exercise to sort of see that we have understood all the details. Okay, but now you see that um, right. So we are doing a reduction here from the non-reachability. So the non-reachability is co-NL, right? It's co-NL complete. It's co-NL complete. So the non-universality becomes co-NL hard, right? But again, like as I said, that because of this Emerman-Zelepsini theorem, which gives that NL equal to co-NL. And hence this is NL complete, this problem. Clear? Is it okay? Any question?
So this is true for both NL and for P space. Mhm. Okay.
Yeah. Okay. Okay. Yeah. Essentially it's the same theorem which will show that like uh, that for this non-deterministic space Turing machines, they are closed under complementation. These classes are closed under complementation. Clear enough? Okay. Now we only looked at the so the decision problems for these NBWs, right? There can be similar decision problems for other kinds of acceptance conditions as well, right? So for example, if you are given, let's say, a parity automaton, okay? So often, like we also looked at some translations from other kind of acceptance conditions, translation to Büchi word automaton. So often it is the case that the optimal algorithms, they follow translation to NBW. Okay, optimal algorithms follow translation to NBW, but it is not the case always. It's not always the case. For example, we saw that if you have an NPW, right, a parity automaton to NBW, right? So this gave, like if you have n states and k indices in the parity word automaton, we saw that the size of the equivalent NBW is of the order nk. But there indeed exists algorithms which can solve the non-emptiness for NPW in n log k rather than nk. Clear? Okay. So, and similarly, we saw that NSW to NBW. What is the size? NSW to NBW? There was an exponential blow up. Non-deterministic street automaton to NBW, there was an exponential blow up. Uh, right? And But one knows that if you are given an NSW, right? If you are given an NSW, one can check the non-emptiness in polynomial time. Okay, one can indeed check the non-emptiness of NSW in polynomial time. So it's not necessary that you always have to construct the corresponding NBW and then check its non-emptiness. Okay, good. So that's the thing. Any question so far about the decision problems?
No.
No? Okay, good. Um, okay, so if there are no more questions, so in the remaining time, we will talk about something called logical specifications for omega regular languages. Okay, logical specifications for omega regular languages. So in general, so what is the idea in general? Mathematical logic. So in general, mathematical logic can be used to describe a set of words over an alphabet. To describe a set of words over an alphabet. So the thing is that if you consider a formula in a logic, then you can also consider a set of words which will be satisfying that formula, right? And a set of words is like a language, right? And and yeah. So, for example, suppose we have a formula to express the second letter in the word is a B for the alphabet sigma equal to AB, right? Now there are a set of words, for example, let's say A, B, A, omega, A, B, B, A, B, omega. So these are words which will satisfy such a formula. Okay, satisfy a formula which expresses such thing. Clear? Because the second letter is a B. Second letter is a B. But on the other hand, if you have B, A omega, this does not satisfy the formula. So the set of such words which satisfy the formula, it forms a language. Clear? So we can say that if phi is a logical formula, then this defines a language of omega words. Language of omega words, which we denote by L of phi. Okay, the words for which phi evaluates to true. What about this lecture? So, I mean, or this remaining part of the lecture. So we are going to identify in the remaining part of the lecture, or at least we'll start towards the direction, identify a logical specification framework to capture precisely. So when I say precisely, to capture precisely the class of omega regular languages. So what does it mean by saying precisely? What do I mean by precisely the class of omega regular languages?
Uh, every language that is definable in the logic uh, can be
Correct.
recognized by NBW and vice versa.
Very good. So every language which can be defined using such a logical specification, like by a formula in this logic, right, which we are going to define this logic, we are going to identify such a logic. There exists and as we say that corresponding to this formula, there exists a language of omega words. And this language is in fact an omega regular language. So which means that an NBW can accept such a such a language and vice versa. Given any NBW, you can actually come up with a logical formula, a formula in this logic, such that a formula phi in this logic, such that L of phi, that means the set of words which satisfy this formula, that can be accepted by an NBW. Clear? So this is the thing. So now let's try to formulate the logic. Let's try to formulate the logic. So we'll see that this logic, the logic formula will be interpreted over the positions of the words. Uh, we are going to use some variables like as we do in first order logic, use of variables x, y, z to denote positions, like to denote a position, like every variable x, y, z, it denotes a position. And then we will have predicates, right? So predicates. So for example, we can have something like a PA of x for all a belonging to sigma. So this is a unary predicate. Unary predicate. The letter, so it seems, so as I said, that x denotes a position. And it says that the letter at position x is an A. Okay. And we also have another predicate, which is the less than. I mean, I'm writing it as x less than y, but it's a binary predicate. So ideally, I should write this as less than x comma y, right? Less than of x comma y. I mean, it's the same thing. So to denote, what does it denote? That position x appears before position y. Okay. So it's a binary predicate. Okay. And another thing, like in any logic, usually the equality is already included. Even if it is not explicitly stated, the equality is included. Okay. Now then, logical connectives. We also have logical connectives, which are of the form not implication by implication, negation, disjunction, conjunction, implication by implication, etc. And we will also have quantifications. There exists for all, etc. For all. So here is an example. Okay, I will just give an example. There exists some x, there exists y, such that PB of x and xy. Okay, so I did not say that next of xy belongs to the language. Next of xy belongs to the language. Huh? So what does it say? So suppose next of xy means, I'll talk about this. Suppose next of xy means that x is a position, y is a position, and y comes after x. Immediately after x. Y comes immediately after x. There is no z in between x and y. Another position, right? So what does it mean, this formula? What does this formula denote?
It means there is a sequence of two Bs. That's
Exactly.
BB.
Two consecutive Bs, right? And B is a letter. And this is a derived predicate. So how can I define next of xy? It's defined like this. X is less than y. And it's not the case that there exists such as a z such that x is less than z and z less than y and z is not equal to x or z not equal to y. Okay, I think this is sufficient. This part should suffice, right? Given the fact that x is strictly less than z and z is strictly less than y. And yeah, right? So this should suffice, correct? Because z, this itself says that z cannot be equal to either of x or y. Okay, good. So I mean, so this is like a derived predicate. I mean, we can just derive it using the syntax we already have. Understood? Okay. So let me not. So this, so let's try to find it out. I'll maybe, uh, let's try to find it out ourselves. So how can I write a formula for such a thing? 0, 1 star, 1 omega. Can you say? Like, can you give, for example, the crucial parts that would be there? Like, how would you describe such a thing? And then we can try to find out the exact formula in the logic sort of that we were trying to describe. 0, 1 star, 1 omega.
So there exists some X such that until that, for every zero, the next one is a one, and for every one, it's a zero, and the first element is a zero. And after that X, it's all one.
Great. So let's try to write it down exactly what you said. So there exists such an x such that first of x, so it's the first element is x, right? So this is again a derived predicate, first of x. It's a derived predicate. So we'll write the derivation later. And what can I say? There exists a y maybe, or you can say there exists another x, right? So this is this position after which everything is a 1, right? Such that for all y, for all y greater than x implies p1 of y, correct? P1 of y. And for all y, so this is also a derived predicate, right? Or I could have just written it in this way. Instead of y greater than x, x less than y. For all y such that x is less than y, it implies P1 of I. And for all y such that y is less than x, y is less than x, and P1 of y implies P0 of z and next yz. Clear? Is it okay? So for every y which is less than x, if this is 1, then the next element has to be 0. Okay, right? Okay.
Yeah. And we need to say in the starting that the first x is a 0.
I think here we want to say first x and P0 of x. So this is something. And we would also like to say there exists some x such that maybe P1 of x and this part, right? What we wrote, I would say, just move it a bit to the right. So I just want to sorry. So I'm talking about this position, right? So I'm saying that if everything which is strictly less than all the y such that P1 of y, then the next element has to be 0. And everything which is strictly less than this x, oh no, sorry. So I'm saying, okay, so this is like everything which is greater than this x for all y such that y is greater than x, this x, right? That has to be, I should put here another this thing. Okay. So is it clear? Like I'm saying that, so you have 0, 1, 0, 1, after 0, 1, maybe after this you have the 1 omega, right? So I'm talking about this one. I'm saying that everything, so this one here, this is the x position. Okay, here everything greater than this, they are ones, like everything here is a 1. And I'm saying everything less than this, if it is a 1, everything less than this, if it is a 1, strictly less than this, then the next element has to be a 0. And I also say for all y, y greater than x, and P0 of y implies P1 of z. I should say, I should quantify this. So I should say there exists a z such that P0 of z and this. And here I should say P1 of z and next yz. There is still something not fully done. So for example, here I should say that if this is not the first element, right? If this y is not the first element. No, okay. So I'm saying, oh no, I'm saying that y is there then after this there exists. So I'm fine. I think we are fine. Okay. So we should just make sure that all the open brackets are closed, kind of. Okay. Is it okay? Do you see any question? So this part is says that the first element is a zero. The first element is a zero. This part says that there exists an x, which is this x, and this is p1 of x, and everything afterwards, right? It has all the y's beyond that, they are ones. And for all the y's which are less than this x, so this is this x. So this x here, this x here is this x, right? It's this position x, correct? So I should use this color, maybe x. So this x is this x here. So everything that is less than this x, if it is a 1, strictly less than, if it is a 1, then there exists a z such that p0 of z and next of yz. So the z is here. If this is the y, then this is the z. And if it's a 0, then the next element has to be a 1. Okay, so this is what we are saying. Clear? Okay. Now consider the following language. Instead of 0, 1 star 1 omega, consider 0, 0 star 1 omega. Consider 0, 0 star 1 omega. The question is the following. Can we now write a logical formula to capture this language? Okay. So that is the question.
Uh, I believe we can't
So
because
what is the problem if we try to follow the previous approach?
there is no notion of this counting two zeros. We can't say for every zero there will be one more zero.
Mm.
Right?
Mm. Yeah, right. So we'll see that whatever we have described so far, we cannot sort of use that to capture this language, to capture this language. Okay. The fact that this says that there are even number of zeros here, there are even number of zeros, right? You have to kind of say that what are we doing? So we have a set of variables, x, y, z, etc. We have a set of such variables. Every such variable denotes a single position. Here we are saying that you have some even number of positions, but there can be unbounded many such positions. There can be unbounded many such positions, right? Such unboundedly many such positions cannot be captured by these finitely many such variables. So that is the problem. So in order to capture this, we will introduce something called set variables in the logic. We'll introduce something called the set variables in the logic, which we'll see in the next lecture, right? And as we try to develop the logic, we'll introduce these new variables called the set variables in the logic. So now the set variables not only will capture a single position, but a set of positions with which we will be able to describe such languages. Okay, so before we finish, what is the derived predicate first of x? How do we define this? How do you define such a predicate, the first of x?
So there does not exist any y lesser than x.
Exactly. y less than x. Okay, so this is the first of x. Okay, so let me end here. Is there any question?
No,
No?
no.
Okay, so that's fine. So I think let me then stop the recording